So yesterday we look at how we can carry out nodal analysis that involve complicated cases of mechanical skin, deviated skin, and the rest. And then we did some sensitivity analysis. I think we still have the plots, go to calculation. Yeah, we still have it. Yes, we could still change this water value and put any water value we have there. We calculate, show results. Then we have our IPR and our VLP. All right, that's what we had. That shows us what our operating point is. Was the gas rate, the liquid rate, as the oil and the water rate. Since water is now flowing, so we have a whole lot of information here to interpret. And all of this depends on the model that you have used, the vertical lift model that you have used, whether it is Hagedorn Brown, whether it is Jones and Ross equation, and so on. So today we'll just look at how we could design maybe one artificial lift, maybe a gas lift method, because I said basically there are three types of artificial lift methods. We have the gas lift, we have the electrical submersible pump, and the sucker rod pump. So we are going to look at how you can design. I'll design one and look at how you can design the rest. If you need data to design any, you can ask. I will always look for some and see if I can share with you. So before we even go to that, let's see if we could just design another type of reservoir, which is not just a simple reservoir, but maybe a dual porosity reservoir. So what's a dual porosity reservoir? That's the first thing we have to ask ourselves. If I go to a PowerPoint, this is a picture of how a dual porosity reservoir looks like. So we have two types of porosity within the reservoir. We have blocks, and these blocks probably are fragmented. And then we have highly conducive path where hydrocarbon can flow. And within the block themselves, they are not that porous. So the porosity here is very low. And the porosity in the fracture parts, they are very, very high. So this is a scenario which is called dual porosity in reservoir engineering because it has two types of porosity. There are basically two parameters that can be used to characterize dual porosity. We have what we call the storageivity. That's the storage capacity of the fracture divided by the sum of the storage capacity of the matrix and the fracture. The matrix and the fracture, and the storage capacity is the volume times the porosity times the compressibility, and also the interporosity flow coefficient. That's the ability of the fluid to flow from the matrix into the fracture. So we have basically two parameters that will define us a dual porosity. So you're talking about dual porosity, these two key parameters have to come in before you can define that. So if I go to my model here, I think I should be seeing dual porosity somewhere. All right, that's my dual porosity reservoir there. Okay. Let's expand this. All right. So maybe we could just make this one simple. Maybe we say no gravel park. Let's just make this one simple. So we say no gravel park. We already developed all of these CSA for mechanical skin, for deviation skin, and for sand control. So we'll just leave it none for now. Then for mechanical skin, we could just enter by hand, maybe enter a unique value that stands for the mechanical skin, not calculating using the Caracas and Tariq equation. So we have our dual porosity, that's our reservoir. There are some few informations that we need to put in. So our reservoir permeability, that is it. Reservoir thickness, we could leave it like that. Reservoir drainage area, we could reduce it a bit, but there's still no problem to leave it like that. We leave that one. Then the production sinks, so you have to give the number of days for which production have lasted. So let's just say 100 days. 100 days. What is the total porosity? The total porosity of the system. They're not talking about the porosity of the fracture or the porosity of the matrix. The total porosity now is, let's just say 0.18. Then the stoichivity factor, we could say 0.2. Then interporosity coefficient, we could say 2 times 10 to the power negative 6. 2 times 10 to the power negative 6. Then we go now to our mechanical skin, things we have highlighted here. Remember that if you're bringing in the aspect of dual porosity, this other part must be highlighted. That means you have to put it. If there's no mechanical skin, you can still put it 0 there. There's still no problem. You see, it turns into green. Shows that there's no mechanical skin there. But we could just put maybe 0.15 there. We could put maybe 0.15 there. All right. So from there now we'll calculate and plot result. Okay. So that gives us our IPR. You have to remember that the IPR are always just looking as if nothing has changed, as if they are the same, but it is not the same. It's not the same. If I go to view results and you look at this variation, you realize that they are not the same. The change with pressure and rate is not the same. And if I now develop my vertical lift performance, I will realize that the point at which they are now intersecting will be different. That means the flow rate will be affected. We have the liquid rate, the gas rate, and the water rate. All of them will be affected at the beginning, at the end of the day. So we may just look at the IPR and just feel that probably is the same, but it's not the same. It's not the same. So that's another small issue. There are so many other types of models here that you could also develop. You may have hydraulically fractured well. That means after hydraulic fracturing, you want to now determine the productivity of the reservoir. The productivity of the reservoir, because you know that once this area around the well bore has been damaged due to skin, I think we specified that type of skin yesterday as the formation damage. That's the type of damage because we have perforation damage, partial penetration damage. So that one is just generalize it as formation damage. That's due to mostly the interaction between hydrocarbon and maybe some other types of fluids within the reservoir that are not compatible. You could have something like fine migration, where finer grains of sand right deep within the reservoir are carried by high flow hydrocarbon. But once they get closer to the borehole, the flow rate may drop and they now deposit the fine grains around that area, thereby blocking the pore spaces and damaging the zone that is closer to the wellbore. So after that has been, if that have been analyzed, probably using a well test, like we did, I think last week we did well testing analysis using Excel, how we could use the pressure and time data that has been collected in order to determine the permeability and the skin factor of that particular reservoir. So if the skin factor of that particular reservoir has been determined by well testing, and it is found that it is very high, this is going a long way to block the pore spaces and hydrocarbon cannot easily flow. So they have to solve that problem. And one of the ways to solve that problem is to carry out what we call hydraulic fracturing. You send in fluid that is mixed with propan. This propan could be sand grain. You inject it at high pressure within the reservoir, and then it creates now high conductive pathways that fluid can easily flow. That's hydraulic fracturing. I think it's part of our internship. for I think week 10, we have to look at hydraulic fracturing simulation using FracPro. So you may have done hydraulic fracturing and you have determined some of these reservoir properties. Then you want to now use these reservoir properties and simulate and see how this fracturing has enhanced the productivity of the reservoir. So you see that at the end of the day, they are talking of fracture height, they are talking of fracture half length, and then they are also talking of dimensionless fracture conductivity. We cannot go into all of this now. I said it's part of our internship, so we are going to do it in a week, I think week 10 or week 11, like that. So we'll not go into that. So there are very different types of models that you can always have around here. So done. All right. So let's see if we could design maybe one artificial lift method. So go to artificial lift. We go back to our first page. We go to artificial lift. Then we may take maybe gas lift. There are two types of gas lift. We have gas lift continuous and gas lift intermittent. So continuous means that you are injecting the gas continuously inside the tubing, injecting it continuously inside the tubing. Intermittent simply means that you are injecting it at interval. Maybe you inject for 2 days and you wait for 5 days, inject again for 2 days. So there's a frequency at which the injection is taking place. So we have two types of gas lifts. We may have continuous gas lift or intermittent gas lift. So let's just probably take continuous. So there are different types of model there also. We have no friction loss in annulus because the gas is flowing inside the annulus. The gas is flowing inside the annulus. I think let's take intermittent, not overcomplicated for now. Let's take intermittent. No, I like it to be complicated. So we have no friction loss in the annulus. So we are just assuming that since the gas is flowing in the annulus before getting into the tubing, there will be no friction loss there, because generally there will be friction loss since the gas is also moving, colliding with each other. There is the molecules are colliding with each other, also colliding with the walls of the tubing and the walls of the casing. There must always be that pressure drop as a result of that frictional force. But we are assuming that there should be no loss in the annulus. So take that, okay. You see that there's an additional term that has now been added at this point. So I will just click on it and then I see the informations and see if I can adjust. Generally, you will not have this gas density. So I am the one that works on this. So you have this gas density, you have to put this value. You have to put this value. You also have to put the depth at which we have the gas lift the operating valve, because there are two types of valves. We have the operating valves and then we have the unloading valves. We have the operating valves and the unloading valves. Maybe I just do a little bit of illustration on that. We have our well ball. We have our well ball. We have our tubing. We have our tubing there. Now we are injecting the gas in this space, this annulus space. Remember that at the beginning of the injection, this space will not be empty, because you don't expect that there should be no hydrocarbon inside the well ball. Before they start designing and implementing the gas lift, they must have shut in the well for some days before they now implement all these things and production starts. So some certain amount of fluid must have accumulated inside this borehole, which generally under well testing, we characterize it as well bore storage. So if there is a particular fluid inside this annulus, before you start injecting, you might say your operating valves is, let's say, at 4,000 feet, but the fluid is at this level. How does the gas now get to this from the surface right to this depth? Because the intention is for the gas to get to the tubing so that it will now mix up with the fluid inside this tubing, thereby reducing the hydrostatic pressure, the hydrostatic head, or reducing the force due to gravity. Because once we have a lighter material that mixes up with the fluid, it makes it to become more buoyant and easily to flow. So what will happen is that they'll have to install what they call unloading valves at this point in time. So they have, or this choosing the depth of the unloading valves is a whole lot of simulation that has to take place, which we cannot go into that. So what will happen is this unloading valve has a particular pressure at which it is operating. That means we have a pressure inside this tubing, and then we have the pressure at this outside part. If the pressure inside this tubing is higher than the pressure at the outside part, the valve is not going to open, it's going to close. But immediately the pressure inside here becomes higher than the pressure inside the tubing, this valve is going to open and fluid will flow. So what will happen is that they will pump the gas at high pressure. The gas will be, as it is forcing down, it now increases the pressure inside this annulus. Then the pressure here now becomes greater than the pressure here. So what will happen now is this valve will open and this fluid will easily flow and then flow to the surface. Then it will push it down onto, it will now come down to below the valves. Immediately it comes below the valve, this pressure now becomes higher, the valves now closes. You now keep pushing until you go now to the next unloading valves. So it now keeps pushing and the fluid now, these valves also open and the next fluid, and the fluid now starts flowing. So you get to a point where you have unloaded all of the annulus onto the liquid level is now below the operating valve. This valve where you have the continuous injection of gas is what we call our operating valve, because this pressure, these valves have been closed already. So this is where we have the injection of gas taking place. So you need to know the depth at which this operating valve is located. That's where we are talking about our operating depth. Then you are talking of the orifice diameter also. I think, let me take this off. Okay, from here, we will just say done. We will just say done. Then we will go now to our design. We'll go to design. Then we are going to see gas lift. That's highlighted. If you have not chosen gas lift in this first part of it, you will not see anything here. Remember, these are the various types of artificial lift method, but they are not highlighted because we didn't choose them. So at this point in time, the first thing first is I think we should do some adjustment. This gas oil ratio is too high. You cannot be doing gas lifting when the gas oil ratio is that high. If the gas oil ratio is that high, then the system should definitely be functioning at natural flow. So if it's not functioning at natural flow, that means that the two curves are not intersecting. Let me see that first. So we go to calculation. We have this. So we change this as 150 and see. And then we do our calculation. So result and plots. All right. So you see what has happened when they have reduced the gas oil ratio, even though they are intersecting at this point in time. But if I look at the liquid rate, if I look at the liquid rate here, the liquid rate has dropped. It has dropped drastically from what we had. So most of the time they may be carrying out this artificial lift method, not only because there is absolutely no intersection between the two plots, but maybe because they are intersecting at a very low rate. That means the flow rate has dropped drastically in such a way that there is no profit on undertaking the activity. So they have to see how they have to increase the rate. So when they say we have to implement the artificial lift, it doesn't necessarily mean that these two must not intersect at all. It might be intersecting at a very low rate. Yeah, so let's see that. So we have inputted all of this. So we go to design. we take our gas lift, and then we take new well. So we want to enter a new well. So you have to enter all of this information here in order to develop the nodal analysis for an artificial gas lift system. All right. So we'll just try one case here. I think I've worked with electrical submersible pump and sucker rod. I've probably not done simulation on this to see how it goes, but I think I have a data here that we can use to try and see how it functions. So we have our design rate method. We have our design rate there. So we have our maximum liquid rate. Maximum liquid rate should be 10,000. 10,000 stock tank barrel per day. 1, 2, 3. We have our maximum gas rate. Maximum gas rate is 4 million of standard cubic feet per day. So we have 4 there. Maximum gas during unloading. That's the unloading period that I've already explained. Maximum gas during unloading, we have 4 also. We have 4 there. We have flowing top node pressure. So we are talking about the wellhead pressure. We are talking about the wellhead pressure, we could say 250 psi. Okay, so we take this 250 psi. Unloading top node pressure is also at 250 psi. Operating injection pressure. Operating injection pressure 1,500. All right, maximum depth of injection. Maximum depth of injection, maybe we're having 8,500 here, but there's still no problem. We used, I think the last case, what I put was 5,000. So let's just put maximum depth of injection around 4,000 there. Static gradient of load fluid. That. Static gradient of load fluid. So we have 0.43. Maximum transfer change in pressure 25%. So our water cut 0.4543. All right. So we have maximum transfer that and the safety for closure. We'll just leave that at 0. Our gas oil ratio just put at 150. Water cut, let's just say 10%. Water cut. Okay. So our design option, I think I have the data for that. Our design option, we have casing sensitivity. All right. So the first there is valve type. That's our valve type, casing sensitivity. The next there is valve setting. All valves spacing, we'll leave it to normal. Injection point is orifice, yes. Injection point is valve, no, orifice. Let's leave it at orifice. Okay, let's see if there's another information there that we need. All right, yes. Valve spacing procedure normal. That's okay. Use IPR for unloading. Use IPR for unloading, yes. Orifice sizing on. Okay, calculate GP at orifice. That's okay. All right. So we could change now our tubing correlation. We could change tubing correlation, hydro. Oh, yes. All right. We could take Beck-Sibrel correlation, pipe, Hagedorn and Brown. I've already explained all of this. All right. Oh, there's data that we have not put. This one is okay.
Is it the design rate method?
Come again.
The design rate method, the first one.
Design rate method.
Yes, is that what is missing?
Ah, okay. Calculate from maximum production. Okay. So it shows that you are actually following. Shows that you are with us. Oh. I actually wanted to design this before the class, but I didn't have time. And the soccer rod form and the other ones are too easy. So you can do that one on your own. Okay, calculate for maximum production. I think we have to enter this data because I have a data for that. Valve selection, manufacturer, valve type, valve specification. Okay, choose a valve from the gas lift data list. Oh, okay. I've seen where the problem is. Cancun. All right. Which type are we using? R20. Anyway, we could still use anyone. All right. What's happening?
This design input, that maximum liquid rates.
Yeah.
Is there anything that's supposed to be there?
Oh, maximum liquid rate. I think I put that now.
No, when we toggled the calculate from maximum production, that's when it's.
Oh, okay. The design rate method. Okay. Once you go to, no, I think it was at user defined. That's why we had that. All right.
Yes.
So if you don't put user defined, it shows that you have to calculate it using a correlation. That's why we're talking of calculating for maximum production rate. But we'll leave it at user design. That one is not the main issue. That's not the main issue there. We have designed this. So let me vertical depth bottom measure. Question about data invalid. For push now above data invalid. The maximum depth of oil injection. I think there's an issue around here. Let me see. Let me put it at 3,000. Let's see. There's an invalid data here. Required GP across. Let me see. Small PSI, but the one should not be an issue. 100, but I don't think it should be an issue. Shows that there's a parameter here that we have to change. The problem now is identifying that parameter. Let's see. Design what? Well. Okay, so I'll come back to this. Let me see. I'll come back to this. I'll change this to, let's say, 10,000. 10,000 feet. That's if type, no friction loss. You already choose that at the beginning. So injection, so at 8,000. Oh, there's an issue. There's an issue. We did not change these parameters. I did not change all of these deviation parameter. So it shows that that's the problem. That's where the problem is coming from. The data is not matching because this deviation parameter that we have here, the deviation parameter, the downhole equipment, all of this is for the data that we have yesterday. So we have to change all of this. They are not matching at all with what we have here. Probably that's where the issue is coming from. And that it cannot work for, it is a little bit more complicated for a deviated well. So it shows that it has to be a vertical well.
4,000.
It's always advisable if you want to start a project, you just start a new project rather than working on what you have already worked on. It becomes an issue. And that's the same thing that happened yesterday when we were trying to produce the IPR. So you take another project and you start working with it like that, it becomes a very big problem. Reservation is okay. All right, our achieving is at 7,500. It's okay. Then we come back here. Our gas leak depth. Gas valve depth cannot be 10,000. We should be lower than 7,500, which is where our tubing is. So put 7,000. Put 7,000. Go to design. Gas lift. And we have the maximum depth of injection. This is 7,000. So you see, once one data has an issue, it becomes complicated and you start wasting energy for nothing. All right, so that's our design. That's our gas lift design, telling us exactly how the pressure is varying inside. So you can look at your key here to see all of these plots, to see what they all represent, So I've already taken time to explain the gas lift. So we already see from here that our actual liquid rate, this is our liquid rate after the gas lifts have been implemented. We expect to have an increase to 2,647.07 stock tank barrel per day. That's the actual oil rate. That's the injected gas rate. This is the rate at which you have to be injecting the gas. Then that's the injection pressure. That's the injection pressure of the gas. So after you have done this, you should be able to bring out this and then you give an explanation on the, I think let's see the IPR. All right, so we'll not actually even see any change there. We'll not actually see because it just looks as if it has not changed as usual, but it has changed. Okay, so this is our endpoint of the calculation to identify all of these things at the end of the day. So what you have to just learn from here is at times you're writing a project and you become so frustrated when you try these things so over and over about 4 or 5 times and it doesn't go and you just feel like you should just give up. The best advice is always start a new project where you want to do an analysis. Maybe we have done analysis for this particular, like what we did the other day and what we have done today for dual porosity and for a deviated well and all of that. And then you want to carry out gas lifting. Now what you have to do is start a new project. Don't go and work on what you have already worked on before, because there are some things that along the line they will not match, and once they don't match, it becomes a problem. Once it doesn't match, it becomes a problem. So what you have to know here is what you need is a design option, you need a design input, and then you also need the current valve type. So this, all of what you have here are well-designed valves, the most commonly used valve that we have in the company. But what actually we're supposed to use for this was supposed to be Camco from the design that we have there. But we have used this, there's still no problem. So whatever valve you use have to depend on probably the area, the field. It has to do maybe in the type of casing that you have and all of that. So there are so many parameters that you have to put in place before you have to probably choose a type of valve that has to be used. But if you're working in a company as probably a reservoir or a production engineer, and you have to carry out this simulation, Your job is not to choose a type of valve that has to be used. So your job is the hotel have to tell you the exact type of valve that they intend to use. Then you now have to carry out the simulation in order to bring out the property or what they expect at the end of the day. Because what the software is doing is simulating what the output will be at the end of the day. If this is the reservoir parameter, then we now inject fluids at this depth, at this pressure, at this rate. We expect that at the end of the day, the liquid flow rate will increase from 400 stock tank barrel per day to about 2,000 stock tank barrel, which is a great increase to the company because it's just close to about more than 5 times what they were producing, and they're now producing per day. So what they would have taken 1 week to produce, they are producing it in a day. So that's what the investors just want to hear. You don't need to go and be telling them how you have to design this and design that. You just need to tell them that you need to put in 2 million. At the end of the day, your money is 10 million. That's their interest. All right, so if you have any question you ask, I've said you can design different types of hello? You can design different types of artificial lift method. You just need to come to the first page. You decide what you want to use. Is the electrical submersible any? So what you just do is I'll produce one for you and send. You can ask. If not, we are good for today.